Hello everyone, welcome to this video. In this video, we'll be solving this question which states that G be a group such that Z of G, which is the center of G, is equal to the intersection of all the centralizers of some elements which are present in G, right? So we already know that we know what is the definition of a centralizer. ZG, which is the centralizer of G. This contains all the elements X from G such that that element commutes with every other element of G, right? This is true for all Y which belongs to G. And if you remember what is the definition of a centralizer of A, this is for one particular element. So it also contains all those elements from the group G such that that particular element commutes with this element A, right? This was the definition. AX is equals to XA for this case. Now in order to show that both of them, Z of G, that is equal to this intersection of C of A for all A belongs to G, we prove the inclusions. We prove that first thing, ZG is contained in this intersection of CA where A belongs to G, and second thing, we'll be showing that this intersection is contained in ZG, correct? This is what we wanted to show here, right? So for the proof here, we first of all consider the case to prove the first part, right? For the proof of the first part, we assume that our element Z belongs to Z of G. Now if we prove that this Z is also a member of this, then we will be done, right? So here let Z belongs to this center here. So we prove that Z also belongs to this intersection of CA where A belongs to G. So according to the definition of the center of G, if Z is there in E, so it would commute with every element of the group. This would be there for all the elements Y belongs to G. So what does it imply? It implies that Y would belongs to the centralizer of Z would belong, not Y, Z. Right, so this Z would belongs to the centralizer of Y, right? And this thing would be true for all Y belongs to G, right? Because this is the condition that we are taking here. So what does it mean? If this is true for all Y, so that means for Y1, for Y2 and so on, this is Z belongs to each one of them. So that means that Z would also belongs to its intersection, correct? So we can write Z would belongs to this intersection of all the centralizers where this A is taken from G, right? This is just a dummy variable to show this thing. So here you prove that Z of G is contained in this intersection of all the CAs, correct? Where this A belongs to G. Let's call this as equation 1. For the second part of the proof, we assume that Z belongs to this intersection CA where A belongs to G, and we will prove that this Z also belongs to the center of G, right? So here for this part, we first of all have assumed that this Z is a part of intersection of C of A, right? So by definition, what does it imply? By definition, it would mean that Z would be contained in C of A for all A, right? Then only it would be there in the intersection. If that is the case, so we can write it like this: Z would commute with A, so ZA would be equal to AZ, and this thing would be true for all A belongs to G. So what does it mean? It would mean that Z belongs to the center of G according to the definition of the center, correct? So what does it imply? It implies that this intersection of C of A where A belongs to G is also contained in the center of G. So mark this as equation 2. So we can clearly say from equation 1 and from equation 2 we have both of them equal to each other. So Z of G is equal to this intersection of C of A, where A belongs to G. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.